Please join me in welcoming to the Distinctive Voices podium, Dean Rafael Bras.
Thank you very much. Good evening. Can you hear me well? Yes. I have to begin with two things. First of all professors move, so I'm going to be moving around. Second, all professors like to grade easy, so everybody here gets an A+. Back there, D- at best. And finally, I was feeling very good to see such a wonderful audience here. And I was getting very pleased until Terry Hartman reminded me that all of you here are those of you that are not in a bar celebrating Cinco de Mayo. Well, anyway, it is a pleasure. It's always a pleasure to talk about Venice. It's a wonderful city, in my opinion, one of the best, if not the best of the world. I really and truly enjoyed there. I've been working in Venice now in this project for about 14 years, to answer a little bit of that. Before you ask me, is this my research? The answer is actually no. This is really consulting work. It is the dream job, to say the least, and I would not change it for anything. So I've been very lucky. How many of you have been in Venice? Why am I giving the lecture then? How many of you have been in Venice in the middle of a flood? Okay, some of you. All right. So some of you have experienced what we're going to be talking about, but as I lead you through the story that I'm going to tell you, and this is really a story, a narrative, let me begin by giving you a little bit of history. And let's begin with the lagoon in the 16th century. Lagoon of Venice. Now, north is there, south is here. It's oriented sideways in here, like most of the maps of the period were oriented. Why? Because the boats always arrive that way, and that's the way you saw it coming in. So it makes sense. It's until modern era that we actually fix north-south orientation for all the maps. But the point I want to say, this is the Lagoon of Venice. It's about 50 kilometers long. It's about 20 kilometers wide. The City of Venice is there. What you can see and observe from here is that a very amorphous, ill-defined barrier island separating the Adriatic from the lagoon. Notice the shapes. I want you to notice something else. In the 16th century, the Venetians, which were quite an entrepreneur group, already had diverted major rivers. Those are diversions of rivers in here, which if we were going to try to do it today, I suspect we will never be able to do it. 17th century lagoon, as it develops 100 years later, you begin to see a better form inlets with clearly 5 entrances in this particular case. You see an additional river diverted to the south of the lagoon. Go to the 19th century. Major changes occur in the 19th century. Again, this is not very clear. I'm sorry. Can we dim the light somehow? Is anybody out there? No? Well, anyway, this is the lagoon. City of Venice is here. This is the Lido Inlet. And what I want to point out is here, this is the Malamocco Inlet, the middle section, and this is the Chioggia. Notice in Malamocco, these two things that you see sticking out there are 2 breakwaters. At that point, they started building breakwaters. Notice now that by the 19th century, there are 3 well-defined inlets in there. Thank you. 3 well-defined inlets. The northern one, Lido, remember those names, Malamocco, the quiz will follow, in the middle, Chioggia in the south. By that point, there were already works to put breakwaters to define this inlet for navigation, and not as clear, but at that point they already had been working in building wave protection barriers all along the littoral, all along the beach line here. So this is again 50 kilometers of work in there. This is the Lagoon of Venice now. Venice, right here. The causeway that connects Venice to the mainland is right in there. The Lido Inlet, north, with breakwaters. You see them defined by the plume of dark water going out in there and with the tides as it moves in and out. The Malamoco Inlet in the center, the main commercial navigation channel for tankers. Tankers will normally come through here, go through a deep dredge canal in there, and then follow this line up to here, which is the industrial site of Marghera, which is going to play a little bit of in our history in there. Notice a few things, I'll repeat. Now there are breakwaters in all three inlets. The rivers remain diverted. You see these straight lines? Nature doesn't make straight lines. It never does. So you can see that this is a very worked lagoon. The message that I wanted to send is that the lagoon of Venice, including the City of Venice, which is many little islands, 130-something islands, if I recall correctly, connected by little bridges, is an engineered environment. This environment has been engineered for the last 800 years. As the Venetians moved to that area of the lagoon, they used to be in the northern side of the lagoon, in the mainland even before that, and they migrated down. Remember the Venetians, which is going to place a little bit of history here, were merchants, and they were the major naval power of the times. They control the seas in many ways through their merchant ships. If you go to many of the islands around the Mediterranean, you'll see Venetian outposts out there, which explain why they diverted the rivers. Anybody wants to guess? Exactly. You don't want, let me repeat, you get an A+. The whole idea here is that the Venetians did not want the lagoon to be silted up by sediment because they could then be attacked by land. And they foresaw that and in fact then proceeded to divert the rivers to prevent the sediment from going into the lagoon. So that's what creates this man-made environment. If the Venetians had not diverted the rivers and prevented the sediment from going in, the lagoon of Venice by now would be quite sedimented. It would look like this, a series of marshes that get submerged with the tides, some of them, and others do not. This is still in the lagoon. There are still remaining areas that are marshes. But the lagoon of Venice is a net exporter of sediment. It loses on the order, one of the few numbers I'll use in here, 600,000 cubic meters of sediment every single year. Net loss. It is eroded away because the sediment normally comes from the rivers, and those rivers now go somewhere else. The end result is one of the problems of the lagoon is the erosion of wetlands. That is very common. Those of you that took a boat trip around the lagoon will see a lot of the shores of these wetlands, these islands that get submerged with tides many times, eroding away, resulting in a lagoon that in its natural condition would be a very morphologically variable place, fairly shallow with a lot of wetlands, some that get submerged, some that do not, some deep areas, canals cut in between the wetlands, to a lagoon that is really more like a bowl. It doesn't have as rich morphology as it otherwise would have. So the present lagoon looks, this is a cartoon obviously, but looks like this bowl. As the sediment erodes, it deepens the lagoon. As it moves sediment out, deepens the lagoon and makes it more smoother, if you want to think of that way, less of the wetlands. The mean depth is actually, the depth normally is 1-2 meters. It's not on the average. There are a few places that are deeper. The canals, navigation canals, are artificially dredged and kept at a certain depth. But the lagoon overall is quite shallow. So to summarize, we have a very engineered environment, engineered over 800 years, massive engineering efforts that has changed what would have been the natural state of the lagoon. It is nevertheless a place we like. And then the question is, how do you preserve it? Well, I'm not going to talk of all the problems of the lagoon. There are many, and I've been involved in practically all of them. I'm going to focus on the floods. But briefly, the whole issue of erosion is being addressed and has been addressed over the years by literally building wetlands and marshes. What is done is you take these areas, you surround them by sheet piles, take some of the sediment that you dredge for the navigation canals, you put them in there, create, in essence, an artificial island, and you wait a few years, and that's the way it looks. It looks great. It's actually the birds and all the fauna comes in quite quickly. With one caveat, you still have to protect the shores. If you don't, it will just erode away. This is a very expensive proposition to do this. I'll give you some numbers in a second. That is Venice quite commonly. Occurring between the period, that's San Marco, in the back. If you, he's gone again. Dim the lights again, it will be nicer. What you hear behind is a siren, which is an alarm. Most of these floods, I started saying, occur between October to March. Why? Because this extraordinary high tides, and those are the words, the translation from the Italian that we use, are caused by astronomical and meteorological high tides, largely the meteorological high tide. What do I mean by that? What I mean is a combination of bad weather, low pressure in the Adriatic and over Italy, but mostly in the Adriatic, low pressure, a lot of wind, either coming from the south or from the north, in essence, upwelling, pushing water into the entrances of the lagoon. That combined with a natural astronomical high tide produces these very large tides that flood the city. The city has always flooded. When you live in the water, you should expect to get wet. The question is how often. If we look a little bit at the history of how often, what you find is that if I plot in a decadal sense, the frequency of high tides, and this is a number that I will explain in a second. This is events larger than 110 centimeters from a given reference point or datum that, as I will explain in a second, is 23 centimeters below water now. So it's a standard. Anything above that, at 110 centimeters, practically the whole city of Venice, not quite all, but almost the whole city of Venice is underwater at that point. So these are significant tides versus what I call the little tides. The St. Mark's Plaza in front of the church starts flooding when you have a tide of about 70 centimeters. This is 110. So this is significantly higher. So 70 centimeters, you will have water in St. Mark's Plaza. At 80 centimeters or 85 centimeters, all of the plaza is full of water. The lowest point in St. Mark's is 65 centimeters, more or less, literally in front of the church. And if you go there under high tides, you will see the water bubbling up. Actually, not a very high tide, 65 centimeters. A normal tide will be on the order of 40 or 55. So it doesn't take much for this to begin wetting somewhere. But here, I am plotting the frequency of events larger than 110, so significantly larger tides than the run-of-the-mill one. The decade from 1923 to 1932, on a typical decade there, only about 2 events occur. If we go to the decade from 93 to 2002, we have 57 events, larger than 110. The trend is clear. These are some of the magnitudes. November 2002, 147. The big one, which caused all this attention to Venice and to Italy, was in November 4th, 1966, when essentially 2 meters of tide flooded all of Venice and threatened at that point to break through the barrier islands. In other words, destroy the lagoon. It got pretty close. I don't know how many of you recall this moment, but I remember, because all of Italy was underwater at that point. It was a massive flood. The Arno River in Florence flooded. It flooded the palace where the museum is in Florence, several meters high. So this was a national disaster all over Italy. And in Venice, people really started getting very scared that the city was in danger. And that's when people started looking seriously, why is this happening? Why do we have this increased frequency of floods? That's when they really started thinking about how do we intervene. So think of it, 40 years ago. It's taken 40 years, it's employment for life. but it's been quite a while. So again, you see this clear tendency of the frequency of floods to increase. So a flood of 140, at which point all of Venice is underwater, used to occur on the average maybe once every 10 years. Now it occurs every year. Every year. It occurred this year several times. I'll show you that later. Why? Why is that tendency occurring? Well, mainly 2 reasons. This is a diagram that shows you years from 1900 to 1990. This is sea level in here, relative sea level. So you have the 0 point there. If you take that point to this point, it's about 24 centimeters in here. That is the relative sea level lost to the city of Venice. So think of it this way. To a person living in the 1900s, the city looked to be 24 centimeters higher relative to mean sea level. But there are 2 components to this. One, which is subsidence, the sinking of the city, and another one that is sea level rise. So let's see a little bit of the subsidence in here. If you go back to the 1900s, the subsidence follows this ochre-looking color. At a rate, the slope of that line, the rate of sinking is about 0.4 millimeters a year. Fairly steady, slow, occurring largely because the clay layers under the lagoon compact naturally. So this is natural compaction of the clay layers. It just goes on at a very slow rate. Then, 1920s, you see that rate of sinking picked up. 1952, that rate of sinking got faster. And it continues down. 1970, it goes up. From 1970 on, a little after that, it continues going down. But notice that the slope of that line here is going down at the same rate as the okra natural rate. So, there's a second quiz. Why? Pumping water. He's answering all the questions. Pumping water. Look at the years. What happened in 1920 or around thereabouts? I'm sorry? Well, not really, but the industry expanded. Why? What happened shortly before 1920? The war. War ends, industrialization began, they started rebuilding, started pumping water in the mainland, by the way. This is largely the industrial areas around the mainland. That created that. What happened in 1952? A few years before, there was another war. They came back and rebuilt even bigger and better. Started pumping water, and the rate of sinking increased. What happened in 1970 when it bounced back? They stopped. You are absolutely right. Why? What? No. He gets an F. The 1966 flood. All of a sudden they say, oh my God, let's study this. They spend 4 years and say, hey, we're pumping too much water. So they stop pumping the water. When they stop pumping the water, it bounced back some, but all of those of you that are engineers or geologists or earth scientists understand that this doesn't recover. It's only a one-way trip. With a little bit bounce back, but it will never recover naturally completely. So what you have is a little bounce back in there, and then from there on, it continues to sink, but at the natural rate. So that's part of the story, and if you go here, you see that of the 24 centimeters, about half of the 24 centimeters of relative sea level loss to the city, about half is strictly due to the sinking of the city, which continues, but not at this rate. In other words, it continues at a very, very small rate, relatively speaking. This rate was 10 times that. Now, what hasn't changed is that. This is sea level rise. Sea level rise, that rate in there is a little less, it's about 1.7 millimeters. In other words, a little over 4 times bigger than the natural subsidence. And it's been going on for quite a while. It is quite consistent with sea level rise that we know is occurring around the world. Now, why is sea level rise occurring? The Earth is warming. I'm not going to go into a debate of why. I think I know why, but that's irrelevant. It is warming. And as it warms, and also the oceans warm up, there are several effects. As the ocean column warms up, water expands. That's the bigger effect. And then if you have ice masses over land, like Greenland or the Antarctica, melting, or glaciers melting, then they contribute to sea level rise. Big debate about how much sea level rise is going to be. But we know it is happening. This is not made up. It is happening practically everywhere around the world. At rates that go between 1, here is 1.7, as far as we can tell at the moment, to as high as 3 millimeters a year measured. So significant variability, but it's going up. That we know. So to us, the threat, the biggest threat at the moment is not the sinking of the city, but is the sea level rise. That is what presents the threat in the future to Venice and to the rest of us to a large extent. I don't know how many of you remember, but there was a PBS special not long ago that the title was, and I remember because I helped them at some point, and the title really made me very upset because it said, Sinking Venice. And I kept saying, but the city is not sinking anymore. That was part of the story, but the future of the story is not that. And if you get anything out of two things that I want you to remember so far of this little talk, is one, an engineered environment. A lot of what we see is what we made happen. And two, the problem of the future of Venice is the sea level rise. It's not that the city is sinking. So next time you hear somebody saying, the city is sinking, you say, no. Okay, so I think that is an important message. So remember, we have lost equivalent sea level rise, and we'll continue to lose it, of about 24 centimeters. Most of that is caused by sea level rise. If you do the multiplication over 100 years, you'll see that on the average, you're going to get about 100 years from now, about 22. If this continues at this rate, about 22 additional centimeters of relative sea level rise. Most of that, about 17 of them, will be really sea level rise. The other 5 are going to be the sinking of the city. All right, so that's what causes it. So what are we doing about it? Well, again, many things. You saw the interventions on building wetlands. This is another type of intervention that is completed. Over 50 kilometers, all these beaches have been artificially being reinforced. So what you see is these groins is the technical term, some underwater groins. You see the channel there, all the way for 50 kilometers. This sand was barged in. The original, to give you a sense of what happened in 1966, you see that dark spot there is the remnants of a tanker that ended up almost going over the wall, which was here. So the sea was to the wall. The normal sea was to the wall at that point. The beach was that narrow. So in order to, this is the narrowest place in the island of Pelestrina. Lido is at the end of that. They widen the beach for protection, and again added these groins to protect against the wave action in there. Expensive proposition. Between making wetlands and building this thing, and a few other things that I'm going to maybe mention as I go along, the rate of expenditure in Venice over the last almost 20, not quite 20 years, been on the order of $100 million a year of construction. It's a great business, Terry. So it is a lot of expensive interventions. It's not cheap, as you can imagine, to intervene to that scale. But I think it's worth it. What else is done? The pavements of many parts of the city are raised to a given level. Normally, it's been determined that you can raise the pavements in many places up to a level of 1.2 centimeters, sometimes 1.10 centimeters. This is 1.10. I'm sorry, this is 1.2 here. This is in the far end near the railroad station, so it's not near the historical center, although for us everything there is historical. But for them, this is just modern stuff. This can be, you see, this hasn't been done. It's being worked on. This was years ago. This has been redone. You raise the pavement. The idea is to protect the flooding, at least of the public areas, passively by raising the pavement in order to keep it dry for most of the small floods. In other words, a flood less than a 1.2 centimeters will not wet this, which is the majority of them. But a flood larger than 1.2 meters or 120 centimeters will still make this wet. So some people suggested at one point, well, look, why don't you just do that everywhere? And the answer is actually quite simple. First of all, it will take the next 100 years to do it, and cost an incredible amount of. But more importantly, and this is the main thing, you're trying to protect the historical city, and that includes the buildings and the facades and all that. The last thing you want to do is raise the front of the facade and cut it up. In fact, as you will notice, some of these doors are getting pretty short. So you have to be a very small person at that point. This is not something that you want to do. In fact, there was an architectural study done where we surveyed and photographed every facade of the whole city and sections and came to the conclusion that in most places it could be safely raised to about 1.1 meters without affecting important buildings, except in San Marco. San Marco, you cannot do it at all, for obvious reasons. And I'll explain that, what was done or what is being done in a second, given that that cannot be done. But the idea of this is to protect the city passively. All right? A lot of effort went to that. So what do we do for the floods that we cannot protect passively? The idea then is to put some tidal gates in the three inlets. Lido, Malamocco in the center, Kioya in the south, remember. Lido, Malamocco, Kioya. Tidal gates are well-known technology. They've been used many times. This is in the Thames, as the title says. When I had that in Italian, I would say, although it's pretty obvious, I would have this as part of my quiz. Where is that? But this is the Thames River, and these barriers have been operating now for over a decade to protect the City of London against flooding from the North Sea. Now, notice the style. No, they were not designed by Frank Gehry. But they look like that. They're essentially these structures, superstructures, and they don't look bad at all, with metal cladding, shiny a la Frank Gehry type. And then they have this half-circle gates that literally roll in underwater and roll out to separate the city from the flood coming in, the tidal flood coming in, keeping the city dry. And it has worked quite well. Rotterdam, Port of Rotterdam. Industrial city. This is a port, an industrial port, one of the largest in the world. Ships go through here. These barriers, as you can see, block the canal when, again, the North Sea threatens, and it's predicted that you're going to flood the port. The way these gates work is slightly different. These gates normally are sitting on land in these large areas here. Let me give you a sense of magnitude of size. This red thing you see there and here is a locomotive. This is the equivalent of an Empire State Building on its side. And the way it works is that they're sitting here happily, and when they need it, because of prediction of flood, they start the engines and push them into the water, and when they get in the water, they fill them with water, so they sink down and close off the canal. Hence separating, that means that the sea can go higher than the water inside. That's the whole idea. What is going to happen in Venice? Well, this is a little cartoon. This is a strategy. Present situation, this is the sea on the Adriatic in here, sitting here. If the flood, any flood that comes in, the level of the lagoon will ultimately reach the same level as the sea, more or less. So it will start flooding at 110. Everything is flooded easily enough. Now, what is planned is a combination, the strategy here is a combination of passive protection by protecting, as I said, raising the pavements, or in San Marco, actually literally building very unobtrusive rising of the sides. And then if you have been there recently, you've noticed that there are sections where this is done already. They took every pavement out, dug it out, and it's like a puzzle. You have to put them back in the same place. So you dig that up, you raise them up, dug it down, put an impermeable clay barrier, a new drainage system, and pumps, and then put the pavement back. A very expensive proposition. And the whole idea is that around San Marco, if you go, you'll notice that the edges are now higher than the center. That will protect the lagoon from coming that way. Any water underground gets caught by the impermeable layer and the drains. So that's the way San Marco is passively kept dry. So for floods less than 110, this is the sort of the cartoon of the passive protection, this ledge line. You let the water in, and it will rise to 110 or whatever, or less than 110, and it'll still be dry. For floods larger than 110, then things get serious, these high tides, and there will be a system of gates where you block the sea, let the sea rise to whatever level it wants to rise, and keep the lagoon at less than 110, so it will stay dry under the passive protection scheme. So that's the idea. How do the gates look? Again, a little cartoon. These gates are the opposite of Rotterdam. Rotterdam, they were sitting outside. I pushed them in, sank them. In here, I am underwater all the time until they are needed. When they are needed, they push air in, water out, and they go from the resting cradle, looks like a cradle, they float out and stick out, separating the sea from the lagoon. Dimensions of this. So they can separate a differential, for example, of 2 meters between the two. Dimensions of this. This is about 30 meters high. So 30 meters are about 100 feet. 20 meters wide and 5 meters, so 17 feet or so thick. Metal construction. It's like a ship. You have metal construction of that nature. It's a steel structure. When you're finished with them, you pump the water in, and they drop down back to their cradle. So they're hinging here. There's a hinge, and everything sits on that. So they just go like this. They're down here. They will get up. The sea is on this side. The lagoon is on this side. All right? So that's the idea. Now, to answer a question, why not do what the Rotterdam people did? 2 reasons. They're ugly This is Italy. And two, there's no land in Venice to waste to put these things outside. There was no place to put them to begin with. Why not do what was done in England? Two reasons. They're ugly. I don't happen to think they're ugly, but really one of the requirements is that this had to be practically invisible. So that was one. And the other reason is that you cannot navigate large tankers easily, or even ships, through these structures that are in the Thames. So it becomes, you could, but it becomes a little more difficult. And that was another requirement. They wanted pretty much unrestricted navigation. So very Italian design. In essence, you don't see them. Even when they are open, in other words, they're operating as a barrier, the most they're going to stick out is 5 meters, 15 feet. From anywhere, unless you're standing next to them, you're not going to see it. It's a very low-profile thing. From Venice, by the way, you'll never see it. There's not a chance you'll see it from Venice. It's too far. So it's really, really quite invisible. We've studied this in many ways. Numerical models, tiny little models, physical models. And over all these years, I say, yeah, this is going to work. That's what the numerical model says. And I saw these little tiny models working, and it may work. I wasn't convinced until a 1 in 10 model was built in a large swimming pool. So this is 0.5 meter thick for the 5 meters of the original one, of the real one. And in there, you can go there and literally see these things the way they work. And you will see one side of the swimming pool with the waves coming in higher than the inside. So you finally say, yes, it's going to work. It's very convincing because the size is quite impressive. Let me go very quickly then. You don't have to memorize this. But I just wanted to show you a plan view of an engineering drawing, and then I'm going to show you the pictures. So I just wanted you to relate a little bit, because you're going to see the elements the real elements. This is the Lido entrance, few elements, an artificial island in the middle. This is the widest entrance, it's about 1 kilometer wide. So there are 20, or there will be 20 flaps of the gates lying on the bottom of the entrance right here, on this side, and about 20 on this side. Remember, they're 20 meters wide. A refuge harbor for little boats that get caught and don't want to stay out here in the middle of the storm. They can come in here. There's a small lock, and you go out that way. A rebuilding of the breakwaters completely. And again, 2020 gates. If we go to Malamocco, the central main navigational area, a massive breakwater here. I'll explain in a second. Rebuilding of these all breakwaters, 20 flaps in what is 0.5 kilometer wide. This is the main navigation canal. So this is a lock, but it's a big lock. This is a lock that can handle the tankers that go into the Venice lagoon. This breakwater is to allow tankers, if they want so, to do so, to still go in the middle of a storm when these things are closed. So they can come in here, operate protected by this breakwater, and go through this lock to the lagoon. Little history. In the original design, the lock wasn't there. But the Port Authority insisted that they wanted to have the ability to essentially have no more delays than just a few hours, no matter what the conditions were. It's not true now, so why you want it then? But anyway, but they insisted. And it shows a little bit of the dilemma of large infrastructure projects. There is a need for them, no question about it. I'm not questioning their desire. But at the end of the game, the log was added because without that, the opposition by the Port Authority would have stopped the project. Cost of that little log, about $200 million. About 100 for the log, 100 for the breakwater. So that's what it costs. Now you say, how can you spend $200 million on this? Well, the total project is about $5.5 billion. So it was either not doing anything or spending the $200 million on this. In Kioja, southernmost, little breakwater here to protect it because there's a lot of waves. This is the hardest wave environment in here. 20 flaps in here, a small refuge harbor, little log for small boats. This is largely for emergency boats and for essentially rescue boats or something of that nature, nothing else. Well, this is the way it looks as of last February. This is Lido. You should recognize that by now. The artificial island in the middle is already done. All these breakwaters are done. So this is the north, this is the southern breakwater. You see where the gates are going to connect right there. That's where the caisson goes to the northern side, connecting to this point, and from here to that point. The refuge harbor is that area here, is filled. I'll tell you why in a second when I show it to you. The back, the lock is in the middle. Moving along, this is the northern side. You see the small locks are in here. The refuge harbor is this part in here, and notice it's filled, and it has this different color material. That is a mix of soil and concrete, very accurately, very compacted. Why? Because the large caissons that are going to go underwater, the big cradles for these flaps, are going to be built here for this entrance, for this inlet. And they're going to be built there. When they're finished, you float them out, drive them out to where they are, sink them in place. So that's the way that this is going to happen. This is, again, where am I? Oh, yeah. This is the island, the connection in here, where the gates are going to moving south. This is the southern part. It's actually beautiful construction. They've done a beautiful job, very clean. This is actually now open. You can walk all the way to there now for the public. And the gates will connect in there. If I go down to Malamoco, main navigation canal, breakwaters built. The main breakwater protecting the area is that one. The log for the ships is here. The gates will go essentially from about there to here, that way. This area is where they're going to build the caissons for this entrance. Again, this is another view of Malamoco, a better view of the big lock in here. This lock, by the way, for about almost a year, was not completed in one of the branches because they found a sunken barge right there. And you say, so what? Well, you don't move anything you find in Venice. You know, the archaeological groups have to come and look at it. And you say, well, was it valuable? Well, it's a matter of opinion. This was a barge of Napoleonic times when Napoleon invaded Venice, which is not that old. It was about 100-something years old, full of stones that were used to build the old breakwater. But literally, the barge had to be lifted out. So they had to build a system that got under and floated this barge out, stones and all. I don't know what they did with the barge, to tell you the truth now, but it's not there any longer. I delayed that for about a year. The south is this, again, the two small locks, the safety harbor where they're going to build the caissons for here. Again, notice land is very, very limited in here. This is a bird reserve. It's a protected area, so this is very carefully monitored all the time. Again, another view, the two logs, the area in there. Notice that the area is not fully dry, and that's because there was, or there is, I think we resolve it now, but there was a problem in that corner. It was leaking through there. But it is actually quite nice. This was this past December 1st. San Marcos Plaza. Never experienced it that way. It's actually pretty sad in many ways. The places that they put for you to walk is more or less where that woman is walking. You see the waves. This is Rialto Bridge. And by the way, the boats are going through. This is people don't realize this and says, who cares whether it floods? Well, I care, but I don't like to get wet. There's another factor. If you get seriously sick in Venice, don't get sick during a flood, because there's no way to get you to the hospital. Why? Because the boats don't fit under the bridges. So you got a small problem. So time your sicknesses. This is the time history of the tides that occur in December, this past December 1st. And what you see is the water reached 157 centimeters. This was a significant flood. If the gates had been operated, is this little black line here, the maximum that it would have reached would have been 95. So that's a simulation of what would have occurred through using the prediction system and kicking the system in as we simulated. One last quiz. Why does this go up after you close? Huh? Rainwater. The two of you get A's. Both rain in the lagoon directly, and actually some drainage from the mainland. And there are about 15 centimeters between each of the flaps. So there's water through at a relatively small, relative to the massive amount otherwise. But it does go up very slowly. Sea level rise predicted by IPCC, the Intergovernmental Panel of Climate Change. The most probable would probably be on that order, about 40, this dark line there. Some people say it's going to be 80 centimeters or even more. Frankly, who knows? All I know, it is happening. I hope it's more like this than that. If it is like this, Venice will be happily forever ever after. If it is like this, Venice will be in much better shape than we are. But it will have to face, at this rate, the problem is that you would have to close those gates very, very often. If you have a sea level rise of 50 centimeters, you would have essentially to close the gates something like 120 times. Actually, more than that. You will have to follow this red line that will project up there. It would be too much. It will certainly interfere with traffic, will change the way you use. But I don't know that at that point there's more choice, to tell you the truth, if that's the case. So what you would have to do, I'll answer, what you have to do is you adjust your operation rule. So if you allow a little bit of flooding, rather than closing at for 110, you close for 120, you get 10 centimeters of water in the low-lying areas, then you can reduce the number of closings quite significantly in here. If you are willing to live with a little bit more flooding, then you can close even less. But my thought on this is that given the realities of sea level rise, the interventions now make sense, even if you have to adjust later. The uncertainties are high, but that is happening is clear. Somebody had a question back here.
Because the gates are underwater, and the ones in Rotterdam aren't, are they more susceptible to saltwater and things like that?
Repeat the questions. Are the gates, are they more susceptible to corrosion because they're underwater? Absolutely. and they're treated in the same way that you treat a chip. So there's cathodic protection, electrical currents built to maintain, control the corrosion. They're painted with anti-corrosion, and they're scheduled to be maintained every flap every 5 years. You pull them out with this neat little barge, not that little. You pull them out and put another one in while that one gets painted. So anyway, so that's I think the future. But I'm confident in all honesty that if we do this, Venice will be preserved the way we know it. And I am sure that it will happen. Right now we're about half of the project is completed. It's scheduled to be completed in 2014. And I hope to be there for the opening. Thank you very much.